Hello everyone. Uh, in this lecture we're going to continue our discussion on functions, and today we're going to discuss concepts related to function call stack and stack frames. And to understand how a function works, we basically first need to understand one data structure which is called a stack. And a stack is basically a data structure that is operating in the background when your program basically calls a function. So it goes from the main function to another function which you may have defined or might have been defined in the standard C library. And the easiest way to understand a stack is to give you the example of a pile of dishes. So a stack is kind of something which could be considered equivalent or very similar to a pile of dishes that you may see in every kitchen. So just as you are washing dishes, you are putting them on top of each other, so you are kind of creating a stack of dishes. Here in C, you are also kind of, a stack is something similar where you add something to a stack and then you add something on top of that stack, and you kind of keep adding things on top. So, putting things on a stack is known as what is called pushing something onto a stack, just as you would push or put a dish on a stack of existing dishes. And every new item that you push onto a stack is generally pushed onto the top of the stack. Now similarly, when you remove something or some dish from a pile or a stack of dishes, you generally remove the item that is placed on the top. So now removing something from a stack is known as what is called popping. So just as a pile of dishes, so the first dish that you push on your stack or pile of dishes goes at the bottom, the next one is on top of that, and the one after that is on top of that, and then the last dish that you place on your stack basically is placed on top. And so stacks in C also operate similarly, and what they kind of tend to follow is something which is called the last in first out way of operating. So last in first out, so the dish that is placed on top is placed at the very end, is also the one that gets removed first. So last in first out, also known as LIFO for short. So that's how things get added to stacks and removed from stacks. And this process of adding something on top of a stack is known as pushing, and then removing something from the top of the stack is what is known as popping. So pushing and popping, and then LIFO is last in first out. Within C, the function call stack also uses something which is similar to a stack. In fact, it uses a stack data structure. And what this stack data structure is doing is that it is working behind the scenes. So it is working under the hood. You don't explicitly see it, but it is working in the background. And when it tends to come up is in situations when you call a function, what tends to happen is whatever is inside your current function. So let's say you are in a main function and you call another function from this main function. What C will do is it will push your current address on top of a stack. So you know that when you are done with your function that is being called, you will come back to this address which will be on top of the stack. So I will show you a graphic example of this shortly as well. So as each function is called, it is possible that it may call other functions. So this is something that does tend to happen, right? And once a function is called, you obviously complete the function and then you have to return from the function, right? Now when you're returning from a function to the function that originally called it, in order to return you will need to know the return address. So you will need to know where to come back to, and that is where the stack is basically useful. So what happens is a function is called. When a function is called, you push your current address on top of a stack. Then you go to the function that is called and then you execute that function, and then when you want to come back, you retrieve the address of your previous function or the function that called this current function. So you retrieve that address from the top of the stack, and then when you get back, you pop the stack and you get rid of the return address because you do not need it anymore, and that is generally done or accomplished using a pop operation. Okay, so again, each time a function calls another function, an entry is pushed onto the stack. This entry is called a stack frame and it contains the return address. So every time a function calls another function, you first push your current address, which is your return address, to the top of your stack. This entry is typically referred to as the stack frame, and the function will need it when it wants to come back to the original function. So if the called function returns, so once you go into that function, you complete it and you want to come back, then the stack frame for the function call is popped. So you retrieve your stack frame and control transfers back to the return address in the popped stack frame. Okay. And each function, so whenever you want to come back from a function, your return address will basically be available at the top of the stack, right? And so as soon as you kind of come back from the stack, you then have to pop the stack and get rid of that return address, because eventually you may have to put something else in its place. Okay, so let's look at a graphic example here. So let's say that we are inside some function, and let's say originally we are inside our main function, and then within our main function we're going to call another function, function 1. So when we get to this line where function 1 is being called, what will happen is our current address will be stored or our call stack, so it will be pushed into our stack. So our return address is basically at the top of the stack. Then we will go on to function 1. Inside function 1, we have a call to another function, and it is possible that from inside function 1 we may call another function. If that happens, what we will do is we will push the address of the current line of function 1 from where we're calling function 2 on top of our stack, and then we will go on to function 2. So let's go back. So on this line 15 we call function 2. Before going to function 2 we push our current address to the top of the stack. So this is where we will come back to. Then we go on to function 2, and then once we complete function 2 we are going to look at the stack, use the address which is at top of the stack to come back to the line where we originally were inside function 1, and then we will pop the stack, and so at that time on the top of our address of our stack will be the return address to the main function. And then once we have completed function 1 and then we want to return to the main function, we can do so by going back using the return address which is at the top of our stack, and then we don't really have to worry about the stack. We can continue to execute the main function. So that's how it generally works. Now one more thing that I want to point out is that the variables inside the function, let's say you go from the main function to function 1. Now the variables of function 1 will not be visible inside function 2. So in addition to pushing your return address to the stack, you also push your variables or your automatic variables which will not be visible inside the functions that are being called. You also put those inside your stack because you will need them when you come back. So in addition to the address, we also push our automatic variables or our local variables onto the stack as well, so we can use them when we come back to a function. So that's how it will basically work. And then once you actually are back into the function and you have popped a function, then the automatic variables can either be retrieved, or if it was a function inside this function which you do not need any longer, once the stack is popped they will be deleted, but you don't need them anymore. So let's say once you go from the main function to function 1, variable A will also be pushed onto the stack, and then once you go from function 1 to function 2, variable Z along with the address of function 1 will also be pushed to the stack. And then when you come back from function 2 to function 1, and then when you're coming back from function 1 to the main function, the variable Z, because once you are down here you will not need it anymore, so it will be discarded once this information is popped, but you will not need it, so it doesn't really matter. And of course one thing that you want to remember is the amount of memory in your computer is finite. So there is definitely a limit to the amount of memory that can be used to store stack frames on a function called stack. So if you have too many function calls, or if those functions have too many variables that need to be stored on the stack frames, and if that information is more or exceeds the amount of memory that you have available, then you will get what is called a fatal error known as a stack overflow, and that can cause your program to crash. So this is something that also needs to be kept in mind. You don't want to keep blindly pushing too much data onto a stack. This was perhaps a bigger consideration when we were working with computers that did not have a lot of memory. But again, still something that you need to know. And even though we have computers with more memory now, we also have much more data that also needs to be handled. So these are things that you need to keep in mind. Okay, so this now is just an example of your call stack. So on this slide and the next few slides, you actually see the books example of a function call stack. So let's look at this particular example. So we have a main function, and this is basically what we're doing is we're just squaring our a variable. We're actually squaring an integer variable. I believe we've seen examples similar to this before. So we have an integer variable a which is equal to 10, and then within the printf statement we have a call to this variable square, which basically takes this integer a, or rather takes a copy of this integer, squares it, and then returns the value which is printed by the printf function. The book basically uses this as an example to illustrate how things work. So let's just quickly look at this example. So let's say that originally in your main function it lies somewhere at address R1, and so let's look at the figure first of all. So let's say in your operating system the main function is at return location R1. So if you do not have anything being called, your current location will be at the top of your stack. So if you are at location R1, you will be that's the information that is kind of stored inside your call stack. The way that I explained the stack was slightly different from this, but it's not too different, it doesn't matter too much. But let's look at this. So you have your variable int a, and so once you actually come down to this line where you're issuing a call to the square function, let's see what happens. Let's say our square function lies at location R2. So this is basically our return location. So we're going into the square function. So what happens is our return location basically gets pushed to the top of the stack. So this is R2, and then this has one variable x which gets pushed onto the stack. So x is just the copy of the variable a. So this is the location that we will return to, and so after the square calculates the square of the argument it needs to return to the main, and so it no longer needs the memory of automatic variable x. So once you actually go into this place and you actually execute your function square, so your square function is executed. You then, once it's executed, you just don't, so this is kind of like your current location. So this thing on the top of your stack is your current location. The way that I explained this stack, I wasn't really worried too much about the current location, and you can think about it that way as well. So in my example, this was basically at the top of the stack. You can work, you can think of it however you like. But so let's just say you are in your square function, you've executed and you've completed whatever you were required to do in the square function. So now you don't really need its address. So You can pop this, so you can get rid of this and come back to this. Now this is your return location where you originally started from, so you can get rid of that. So pop that, get rid of the variable x. Now you look at your return location and this says R1, which was over here, so you go back to your location R1, so you kind of come back here. So that's the book's example. So it kind of illustrates how the call stack operates. So just by giving you a slightly different example and a slightly different illustration than the one that I gave you. Okay, and so that's just the call stack and stack frame. So a useful concept, something that you need to know. Next thing that we're going to talk about is headers, and we've looked at headers before. So each standard library that we have used has its own header. So things like stdio.h that we've used, maths.h is another header that we have used. So maths.h basically is a standard library that contains functions that are related to maths and mathematical operations. So now the maths.h header, basically what does that contain? Well, it basically contains the prototypes of all the functions that are in this library, and it also contains the definitions of the various functions that are inside this library, right? You don't see them because you just have to use them. So if you want to use them, you don't have to actually go and see them, but you know, the header is basically, that's what it contains. So let's look at some of the header files that are typically available in C. So you have assert.h, which basically contains information for adding diagnostics that aid program debugging. You have some other ones as well. These are all listed in alphabetical order. You may or may not use them, but you know, we've used some of them at least. We've used maths.h, which contains function prototypes for math library functions. We have used, we may use the stdlib. We haven't used it so far, but it contains function prototypes of conversions of numbers to text and text to numbers, etc. So it contains different things. We've used stdio.h. String.h is also useful. So this contains functions for processing and handling strings, and we'll talk about that in later chapters maybe. Another thing that C allows you to do is to define your own headers as well. So you can create a bunch of functions and put them inside a header file, and if you want to include that header, so if you wanted to create maybe a header containing just your square function, you can do that, and then if you want to include it, you can include it using the square dot include hashtag include square dot h directive. So this is something that is useful. So that brings us to the end of this particular lecture. So I'll give you a hands-on demo now, and then I'll see you next time in the next lecture. So thank you.